Hi. I've had a lot of questions on problem 31, so I'm going to demonstrate for you problem 31 of how I would go about it. Basically you can read along with me. Pause the video if you want to, because some things I've calculated really quickly and things like that. So pause if you want to try and do it yourself before you see me do it. Okay, so number 31 here says a projectile is shot from the edge of a cliff 125 meters above ground level with an initial speed of 65 meters per second and an angle of 37 degrees with the horizontal, as shown in the figure, blah, blah, blah. And they give you a picture there that looks something like the board that I have. So for part A, it says determine the time taken by the projectile to hit point P at ground level. So here is point P right here. We are looking for the time right now, so I'm going to put a question mark right there. That's what we're looking for. And then here's the picture of pretty much what it shows you. We have a projectile is getting launched with an initial velocity. It looks like this. This is the path it takes, and in some time it hits point P. Now, they also give you that the height is 125 meters. They give you the angle here. They give you 37 degrees is the angle that the projectile is launched with respect to the horizontal. And they also give you the magnitude of the initial velocity, or the speed, which is 65 meters per second. So 65 meters per second is the speed at which that thing is launched. Now the velocity is going to be a vector quantity that's equal to 65 meters per second at 37 degrees with respect to the horizontal. So that's the vector quantity, but the speed or the magnitude is just 65 meters per second. Okay, so we want to now solve this to find time. And we want to use our kinematic equations to solve this. But in order to do that, this is a vector right now, and it's at this weird angle. We can't solve kinematic equations at weird angles, or we could. It's just going to be very, 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 very difficult. And to make our lives easier, what we do is we find out the components of this vector. So what are the components of this vector in the x direction? So I'll call that v naught x. And what's the component of that vector in the y direction? I'll call that v naught y. So I got v naught x and v naught y. And what these are is they're basically different ways to represent this vector right here. This initial velocity vector. Is I'm going to say, as opposed to saying the initial velocity at 65 meters per second with 37 degrees with respect to the horizontal, I'm just going to say, that's v naught x this way and v naught y that way. That's the other way that I'm going to talk about it. Now, I know the initial velocity vector. I have to be able to find out to split those up into its horizontal components and its vertical components. So the horizontal initial velocity vector, initial velocity component, and the vertical initial velocity component. And here, if you recall from what we did Thursday and Friday, is that we saw that if I added v naught x plus v naught y, I'll get v naught. And using trigonometric equations, we got these formulas right here. So I'm just going to use these formulas for this time. Basically, it says to find v naught x. I basically multiply the magnitude of the velocity, 65 meters per second, times cosine of the angle, which is 37 degrees. So that's 65 meters per second times cosine of 37 degrees. That's going to give me my v naught x. To get v naught y, it's again the magnitude of the initial velocity vector, 65 meters per second, times sine of the angle, which is 37 degrees. So I got 65 meters per second times sine of my angle, which is 37 degrees, and that's going to give me a new equation. And if you calculate that, you will find that v naught x is equal to 51.9 meters per second. And v naught y is equal to 39.1 meters per second. Again, this is v naught x, and this is v naught y. So now that I know these, now all my vectors and everything else is in some sort of, it's either along x or along y. So my vectors now are either along x or along y. And that's how I want them, because now it's going to make calculating them much easier. So what am I looking for? I basically know now, so I don't know delta x. Delta x would be this quantity here. I don't know that, but I'm going to assume that the problem's probably going to ask me that at some point. So I don't know delta x. I do know delta y. Not only is it 125 meters, it's negative 125 meters. Negative because it starts here, here's my origin, and it goes down. It's pointing in the downward direction, so this is going to be negative 125 meters, because the displacement has both direction and magnitude. So now my initial velocity along x is 51.9 meters per second. My initial velocity along y, as I just calculated, is 39.1 meters per second. So let's look at some other things that I definitely know to be true. I definitely know that acceleration along x is 0 meters per second squared. Almost always is this going to happen. Almost always. Ridiculous situations are the only way that it's zero. Always assume 0. Okay, so acceleration along the y. Again, we have this g vector, this acceleration due to gravity that acts on all objects. So this is going to be negative 9.8 meters per second squared. That's the acceleration due to gravity. And negative because the acceleration is always pointing downwards, and we consider downwards to be the negative direction. And I'm looking for time. So those of you who may, let's point it out right now. We know that the acceleration is 0 at every point along this projectile. Every point along this projectile, the acceleration is 0 in the x direction. So that basically means that it's that the initial velocity here is going to be the same velocity here. Vx is equal to v naught x here. Here it's the same thing. Vx is equal to v naught x. Here it's the same thing. Vx is equal to v naught x. Here it's the same thing. Vx is equal to v naught x. Here it's the same thing. Vx is equal to v naught x. Why? No acceleration. If there's no acceleration, there's no change in velocity. So the velocity stays the same throughout there. So I can basically say, at any moment you want to talk about this projectile, the object, when it's in the projectile, it's going to be 51.9 meters per second. And just to double check again too, does this make sense that this is positive and that's positive? Yes, it does. This is going to the right, this one's pointing up. Those are both positive directions, so we're good. Now, let's look at, so now I have my equations, right? My kinematic equation. So it's going to be v equals v naught plus at, and then I have v squared equals v naught squared plus 2a delta x, and then I have delta x is equal to v naught t plus 1/2 at squared. So then I got to ask myself, which one of these? And they're both in the x and y direction. There's x versions of these and y versions of these. And so I asked myself, well, which one should I use? Well, here I have 3 bits of information. I know my displacement, I know my initial velocity along y, and I know my acceleration along y. And then I'm looking for the time. Well, that makes this very useful for me. I know my y, my y displacement. Basically, it says negative 125 because to reach point P, I need to go down 125 and to the right delta x. So that's why the negative 125. So negative 125 there. The initial velocity, the initial y component of the velocity is 39.1 meters per second. And I know my acceleration along y is negative 9.8 meters per second squared. So I'm going to use this. That's where I'm going next. So I'm going to use delta y is equal to v naught t plus 1/2 at squared. And I know usually I say solve it in variable format, but this one's going to be a bit strange. So my delta y is equal to negative 125 meters, which equals my initial velocity, velocity in the y direction, the y component of my initial velocity, is 31.9 meters per second. So that is 31.9 meters per second. T is my variable. And then I have 1/2 times negative 9.8 meters per second squared. My acceleration along y is negative 9.8 meters per second squared. And then now t squared. So I have a t squared and a t. So I can't really combine any of these yet, but I basically realized that I have a quadratic. So I'm going to set the one side equal to 0. So I'm going to add 125 meters here. That's going to go away here. Add 125 meters. I'm going to have 0 equals, I'll do it so that 1/2 times negative 9.8 is negative 4.9 meters per second squared times t squared. Then I have plus 31.9 meters per second times t. And now I just added 125 meters there. There we go. So now I have this quadratic. And to solve it, I can use the quadratic formula. That's the best way to go about this. You could factor this, but no, you probably can't factor this. It's probably impossible to factor. So I'm going to use the quadratic formula, which basically tells me that t is equal to negative b plus or minus, you know what, I'm just going to put in the values. Hopefully you know what the quadratic formula is. If not, pause this video and look it up. So my b term is here. Here's b. Here's b. Here's a. And here's c. So it's negative b, so I got negative 31.9 meters per second plus or minus the square root of, here's where all the negatives and stuff are very, very, very important. So I got b squared, that's 31.9 meters per second squared, minus 4 times a, which is negative 4.9 meters per second squared, and then times c, which is 125 meters. All of this over 2 times a, which is negative 4.9 meters per second squared. You calculate this and you can find the time. You'll get 2 answers. One of them is going to be negative. And the negative one is the one you're not going to use. No negative time. So we are going to use, the one that I get. Again, pause the video, try calculating this yourself. You should get 2 solutions. One of them should be 10.4 seconds. And there you go. That's how long it takes for this projectile to be launched at 65 meters per second with 37 degrees with respect to the horizontal, to go all the way there and reach point P, or reach the ground of this cliff. That's the amount of time it takes. 10.4 seconds. So that is part A. There's part B, C, D, yada yada. So part B. Now the thing is that usually now the problems get a little bit simpler. After the initial problem was solved, the other problems get a little bit simpler. It says determine the range, x, of the projectile as measured from the base of the cliff. The range, they mean this. They mean from the base of this cliff here to here. So essentially what I'm looking for is delta x. How much in the horizontal direction did this object travel? And once I do that, so I can find that by basically finding my displacement. I'm now looking for this. I'm now looking for how far in the x direction did this object have to go before it reached P. And so the only equation, again, because the acceleration cancels out the other ones, leaving you with kind of meaningless equations, the only other equation I have to work with delta x is equal to v naught times t. This is really the only equation that I have to work with the horizontal because the accelerations along x are 0. And then, and so it only leaves me with really this to work with. So that's the equation I'm going to use. Again, I don't need to draw a picture again. I don't really need to label anything unless they give me some new information. So I already have my picture and my labeling. That's why I did it in the first place. So now when I do the rest of these problems, I have everything all organized in a nice fashion. So I have delta x equals v naught x times t. This is, by the way, v naught x times t. Not just v naught. So it's very specific to the direction in which we're working with. So delta x is v naught x times t. Well, I know all this. I know the time. The time to reach point P is 10.4 seconds. And then v naught x, I found that out a long time ago. That was 51.9 meters per second. Oh, this is just a one equation and I'm done sort of thing. So this is 51.9 meters per second. And then t is now going to be 10.4 seconds. My units cancel out. And I get delta x is equal to 540 meters. And I get positive 540 meters. Does that positive make sense to you? Why, yes it does, Mr. Fournier. This starts at 0, it goes to the right. Boom, right there. There you go. It's in the positive direction. So positive 540 meters makes sense. Awesome. All right. And that's that. That was it with part B. So part C, we want to find the horizontal and vertical components of the velocity. So we want to find the horizontal and vertical components of the velocity. I'm going to erase this part right now so that I can show horizontal and vertical components of the final velocity. Basically, what's happening is this thing is getting shot off at 65 meters per second at an angle of 37 degrees with respect to the horizontal. It's shooting up, and then its velocity component, it starts like this, and then it starts moving like this, and then it starts moving like this, and then at this point, just before it's about to hit the ground, moments before it's about to reach there, it drives into the ground. So my velocity vector should look something like this. That's my final velocity vector. It looks something like that. The final velocity vector looks something like that. And it is going to have components of the final velocity along x and the final velocity along y. Now, you already know the final velocity along x. 51.9 meters per second. Why? The acceleration the whole time along x is 0 meters per second squared. So half of the problem's already done. I know my velocity along x. My velocity along x, so this is part C. I already know that my velocity along x is equal to 51.9 meters per second. Because it never changed. It never changed. Now my velocity along y, that did change. And I'm going to need to use another one of these kinematic equations to solve for it. Now, what do I know? I know time now. I know the acceleration along y. I'm looking for this. I know this. And I know this. I know everything. So it doesn't matter which equation I use. I'm going to use the easiest one, the first one. So the first one basically states that Vy is equal to V naught y plus the acceleration along y times t. So that's what I'm going to use for the to find Vy. V naught y already calculated. That's 31.9 meters per second. So Vy is equal to 39.1 meters per second. I'm going to add that to my acceleration along y, which is negative 9.8 meters per second squared. And then I'm going to multiply it by the time, which again, it's the time at that point, at point P. The time at point P, I calculated a while back in part A, was 10.4 seconds. So, 10.4 seconds. The seconds cancels with the seconds squared here. You multiply along there, and I'll basically get that the velocity along y the velocity along y is negative 62.8 meters per second. I get negative 62.8 meters per second. So there's my velocity along y. My velocity along x was again 51.9 meters per second. Now, do these signs make sense to us? Does positive velocity along x make sense to us? Well, if I look at my diagram here, this is going in the positive direction along x. So positive 51.9 meters per second, yes, that makes sense to me. Negative 62.8 meters per second, does that make sense to me? Well, my velocity vector along y is pointing downward. In order to reach this vector, I need to go x in the right direction and then y in the down direction. And so, yes, that negative makes sense to me. And it's very important, especially when we go to calculate our angle. All right? So that's that problem, though. That's that part. That's part D is, that's part C, the horizontal and vertical components of the velocity. Vy, the vertical component then is negative 62.8 meters per second. The horizontal component is 51.9 meters per second. Finally, we get to part D. Part D says for me to calculate the magnitude of the velocity. The magnitude of this final velocity. I want to find its magnitude. And again, like we saw on Thursday and Friday, to calculate the magnitude of any vector, if I know its components, I'm just going to use Pythagorean theorem. Because if I took this vector and stuck it here, I would get essentially that and that. I have this triangle, and I can essentially, it's a right triangle, and I can use the Pythagorean theorem to solve for it. It basically says that the magnitude of my final velocity squared is equal to the x component squared plus the y component squared. And then if I just solve for this, I'll be able to find it. So I'm going to take the square root of both sides, so I'm going to do that. My x component is 51.9 meters per second, 51.9 meters per second squared. Plus, my y component is negative 62.8 meters per second squared. And then that basically tells me, all right, so I do that. So I got this is equal to, and then you just calculate it, and you should find that magnitude to be 81.5 meters per second. So the magnitude is 81.5 meters per second. And then next, so that's the magnitude. Now, and they always usually want this, now I need to, time to go to the next class. Now they want me to find the angle made by the velocity vector with respect to the horizontal. So now I'm looking for this. I'm looking for this angle, theta. I'm looking for theta. Theta is the angle with respect to the horizontal that the vector is going with. Hopefully I'm going to get a negative angle. That's what I should get. And then again, the convention is to use, this is for now part E, the convention is to use theta is equal to the inverse tangent of the y component over the x component. Again, this all just comes from trig, but that tends to be what's used. So I have theta is equal to the inverse tangent of my y component is negative 62.8 meters per second. Negative 62.8 meters per second. And my x component is 51.9 meters per second. Units cancel out, which is good. You calculate it, and you should get, if you are in degrees, you should get negative 50. So this means that theta should give me negative 50.4 degrees. Or at least that's what I got. Negative 50.4 degrees. So my velocity vector now, I can essentially say that the vector, so I could even take away this and say that the vector is 81.5 meters per second. That's its magnitude. And it points at an angle of negative 50.4 degrees with respect to the horizontal. That's its direction. Yeah, okay. So that's that part. And finally, it asks me for part F, find the maximum height above the cliff top reached by the projectile. So this now means that things are going to kind of change around a bit. And to do that, I'm going to erase this. So we can do this is that now we're not worried about point P anymore. We're worried about a different point, a new point. This new point occurs right here at the top, at the peak. Now it's saying, what's the height? What's the maximum height it reaches from here to here? We basically want to know, what's this new delta y from here to here? What is this new delta y? We'll call it delta y2. This new delta y now, we don't know what it is, but we can find it. Now here's the point we're focused on. We're not focused here anymore, we're focused here. So I have a new delta y. I'm just going to keep using this. Okay. We have a new delta y. We don't know what it is. We're looking for it. We're looking for this now. We don't know what it is. And I'm just going to focus on the y components here. Did the initial velocity change? It did not. The initial velocity does not change. It's still being shot off with a y velocity component of 39.1 meters per second. Did the acceleration due to gravity change? No, it stayed the same. That means that if I just know one more bit of information, if you know 3 bits of information, if I just know one more bit of information, I can solve for this thing. And what do I know? The initial velocity, or the final velocity at the peak. What is the vertical component of the velocity at the peak? What is it? What's the vertical velocity of this component at the peak? Just like an object that we throw up in the air in one dimension, its velocity at the peak is 0. Now, this does have a velocity. It has a velocity in the horizontal direction at the peak. But that's what makes breaking these things up into components so useful. The vertical component of the velocity is 0. So this vertical component is 0 meters per second, and now I can solve for this thing. I know my initial velocity, my final velocity, and my acceleration. Initial velocity, final velocity, and acceleration, and I'm looking for this. Awesome! Here we go. So I'm going to use V, this is for part F, finally, Vy squared equals V naught y squared plus 2ay delta y. And I'm solving for this, so I'm going to isolate the variable right now. That means I'm going to subtract by V naught y squared. That's going to cancel out there. I'm going to subtract by V naught y squared here. So I have Vy squared minus V naught y squared, and that's going to equal 2ay delta y. To isolate delta y, I divide by 2ay. Those cancel. Divide by 2ay. And so now I'm left with delta y is equal to V naught y squared minus, Vy squared minus V naught y squared all over 2ay. That's it. Yeah. Okay, now I plug everything in. Delta y equals Vy, as I just said, 0 meters per second. So this is 0 squared minus V naught y, as we said before, is 39.1 meters per second. That did not change. Squared all over 2 times the acceleration along y is still negative 9.8 meters per second squared. And then I do math here. This negative should cancel with this negative, which is good. And I do the math there, and I should get 78.0 meters. That's what you should get. So, A lot of work, I know, but definitely doable if you break it into little chunks. That's what makes breaking up vectors into their components so useful. I can then solve these kinematic problems just as if they're just two one-dimensional problems. And then I combine them together depending on what the problem's asking for. So I hope that helped. Please come to class with any extra questions you may have. And okay, thank you.